In order to determine the elongation of a square hollow bar when it is subjected to an axial force of 100 kilonewton, moreover, if the force is increased to 360 kilonewton and released, to find the permanent elongation of the bar from the data given to us from our stress strain diagram as shown in the figure, we can start by first figuring out what elongation is in terms of a strain. Since we know a strain is equals to elongation divided by the original length, so in order to get the value of elongation, first of all we have to calculate the strain value. Now, this is the strain value that will be happening at a load of 100 kilonewton. So our load value can be related with the stress. So since we know once we apply the load of 100 kilonewton, stress will be generated in that square hollow bar, which can be calculated by our formula of stress is equals to force over cross-sectional area. So here we have a force of 100 kilonewton, and the cross-sectional area of the square hollow bar can be calculated by subtracting the area of outer square, that is 50 millimeters by 50 millimeters, minus the inner square where the thickness is 5 millimeter on each side. So the inner square will be 40 millimeter by 40 millimeter. Simplifying, we get our value of stress as 111.11 megapascal. Now, since that value of stress is less than 250 megapascal, that is our yield stress, meaning that the elongation will be temporary elongation, and we can also apply our Hooke's law for the linear elastic zone. So our Hooke's law is given as stress is equals to Young's modulus times strain. Now, based on that, we have the value of stress and we want to calculate the strain, but we have an unknown value of Young's modulus. So the Young's modulus can be calculated by taking the slope of the linear elastic zone of the stress strain curve as shown in the figure, which we can do that by taking the rise over run. So 250 minus 0 divided by 0.00125 minus 0 will give us the slope value that is coming as 200 gigapascal. Now, once we have the Young's modulus, we can go ahead and plug that into our Hooke's law expression and solve for a strain. So stress is equals to 111.11 megapascal equals to the Young's modulus of 200 gigapascal times a strain. Simplifying, we get the value of a strain as 0.5556 10 raised to power negative 3 millimeter over millimeter. So here the strain is the unitless quantity. However, by convention, we need to put the units in which we are working here. So we have millimeter over millimeter. Now finally, solving the elongation, since elongation is equals to a strain times the original length, here the value of strain is 0.5556 10 raised to power negative 3, whereas the original length of the hollow bar is 600 millimeter. Multiplying the two give us a value of elongation equals to 0.333 millimeter. Next in the problem, it is mentioned that when the force is increased from 100 kilonewton to 360 kilonewton and is being released, figure out the permanent elongation of the bar. Now, here to keep in mind, whenever we go beyond the yield stress or beyond the yield point from the stress strain curve, we go into the permanent deformation zone or in the plastic deformation. So first of all, let's figure out what is the actual value of a stress that will be developed in the bar when we apply a force of 360 newton. That will help us determine either we are in the elastic zone or the plastic zone. So applying our formula of stress is equals to force over cross-sectional area, we get get our value of stress as 400 megapascal. Now, since this value of 400 megapascal is greater than 250 megapascal of the yield strength of the material, it means that we are in the permanent deformation zone or the plastic zone. So let's go ahead and figure out the value of a strain that will be developed when we apply a value of 400 megapascal. Now, from the graph, we can extract out the value of a strain using the interpolation function. Since I know my stress at the very end at 500 megapascal, and the value of his strain is given to us as 0.05 at that point, whereas at 250 megapascal the strain is given to us as 0.00125. So in between these 2 points, any point can be extracted out using our interpolation function. So simplifying, we get our value of a strain at the value of 400 megapascal equals to 0.0305 millimeter over millimeter. Now, this strain is the total strain in the bar that will happen when a force of 360 kilonewton is applied. However, in the problem, it is mentioned that this force is released, and due to the release of the force, some of the strain value will be recovered, which we can represent as epsilon r. This is the elastic deformation, that is the recoverable deformation. However, some of it will be permanent because we are above the yield point, that is given as epsilon p. Now, the recovery part have the same slope as the linear elastic zone. So we can represent the slope of the recovery path as the value of E that we have already calculated of 200 megapascal, which means that utilizing that value, we can figure out the recover strain. So our value of stress is 400 megapascal, our Young's modulus is 200 gigapascal, and the recover strain is coming as 0.002 millimeter over millimeter. Now, since the total strain value is a sum of the recover strain as well as the permanent strain, we can figure out the permanent strain value by subtracting the recovered strain from the total strain. Simplifying, we get a value of our permanent strain equals to 0.0285 millimeter over millimeter. Now, once we have the permanent strain, finally we can figure out the permanent deformation. If you recall, we talk about strain is equals to deformation over the original length. In this case, the permanent elongation is equals to our permanent strain times the original length of the bar, that is 600 millimeter. Multiplying the two give us our permanent strain of 17.1 millimeter.